Good afternoon, and let me begin by thanking the organizers for inviting me to talk to you about these very interesting topics. I've been tasked with stirring the pot a little more on neutron stars, so don't expect too much vacuum in this talk. Although people have already brought up facets of the physics we have been able to pursue with these binaries in previous talks. So I'm not going to, I'll limit myself in reminding you about all those details. I'll focus on a couple. But basically, yeah, a lot of physics has been extracted from neutron star binaries. There was a talk by Ish early on, and then Kenta, Paul, I'm missing some names, I know, then Varun Bhadaro yesterday, but also Saurav Chatterjee, Mukherjee, no, Shubhadeep Mukherjee this morning. So, they all talked about certain aspects of binary neutron stars. I'll focus a little more on how successful we have been in constraining certain aspects of the neutron star equation of state with multi-messenger observations. What else remains to be done on that front and others, we'll see. What are the prospects going forward with the planned proposed gravitational detectors as well as telescopes? Measuring the EOS more precisely, yes, but can we start constraining the population of neutron stars, so demographics? Maybe even find some ways of limiting the behavior of how these binaries evolve back in redshift, right? Can then, in turn, feedback with the equation of state to help us do cosmology with these objects, regardless of whether they're bright or dark. In fact, if you think about it, so yeah, Ish told us some numbers with regards to the Cosmic Explorer detectors in how successful they will be in observing binary neutron star mergers as a function of redshift. But for his mass radius plots, he was limiting those 100 observations to relatively close distances, about 450 megaparsecs or so. But Einstein telescope and Cosmic Explorer will see these objects much farther in redshift, beyond even a redshift of a few. The problem, of course, there will be, would they have electromagnetic counterparts that are bright enough to convey enough physics information to us? Gamma ray bursts, yes, we see short duration gamma ray bursts, the counterparts of these mergers, right, up to known redshifts of 2.2-ish or so. But then we do have certain problems with gamma ray bursts. It's not easy to localize them, to therefore even find the host galaxy. So how do you get a redshift measure? So these additional detectors are great, but they also bring their own sets of challenges, which we'll have to start preparing, and some of you already started that. Maybe I'm late in the game, in how to actually be able to extract that physics from them, right? So this talk is not going to answer all of these questions, but maybe it will provide enough food for thought and discussions later. And then, okay, what are the future challenges can we think of? So when it comes to doing physics of high density nuclear interactions, looking for phase transitions, again, in the core of neutron stars, so nucleonic matter transiting into deconfined quarks. Is this possible? Do we see any hints of that happening today? If not, how can we tease out this information? But with the, is it few observables that maybe we will be afforded? Kenta showed some nice numerical relativity simulations with magnetohydrodynamics, which suggests that no, the observables may not be limited to just the tidal deformity of neutron star macroscopic parameter. There could also be tidal heating because of dissipation in the presence of hyperons. But what kind of signatures would they leave on these multi-messenger channels, right? In gravitational waves, perhaps there will be some tweak in the waveform evolution, but will there be anything else in the electromagnetic emission to corroborate the gravitational wave signal? But then for data analysis, what can we imagine for difficulties that may crop up? You already heard, maybe it was in one of Frank's talk perhaps, that we will be looking at signals that are now 400 times longer in time, right? So how do you do data analysis? Do we actually have solutions to this yet? We are getting there. Interestingly, there's already a paper out from the Glasgow group, which is another paper using machine learning techniques, but now tackling this problem pretty much head on. There were many machine learning solutions that have been proposed for not just the detection of binaries, but also doing parameter estimation with binary signals. Some for binary neutron stars, a lot for binary black holes, simply because binary black hole signals are shorter, easier to compress in the data space. But now we at least have a few papers that are tackling these long duration signals, how to compress them more effectively and still be able to dig out enough physics from them. With detectors, this also has come up, can we be smart in how we use them, whether it is by narrowbanding one of them in the mix, like Ish pointed out, there is this 20-kilometer configuration in Einstein telescope that could essentially be devoted to be able to see the post-merger signal from binary neutron stars at high frequencies. That may be our only way in gravitational waves to be able to understand or detect the effects of a hot equational state, okay, where maybe some of the neutrons become a non-degenerate, but also perhaps other kinds of phase transitions may kick in. Some numerical simulations have been done with that kind of an equational state, such as by Rezzola and others. I'm not going to talk too much about it, but we can take that in the panel discussions. If you want to see dynamical tides, these are weak effects, which means, again, you're asking a little more from your detector to be able to unravel them. And also because these may really be heightened in the last several cycles before merger, right? But there are other things that can confound our effort here, and one of them you have just heard in Basu's talk. What if some of these neutron stars have dark matter in them? That is, that's my nightmare. That's the last thing I can hope for. We are struggling to constrain some of these nuclear equational state parameters I will show in a few minutes. But if there's dark matter in the mix, I think all hell breaks loose. Is broken loose as far as I'm concerned. But then Basu also talked about, there is a plethora of possibilities as far as dark matter particles go. But then, you can be a little more lax with what kind of other interactions you bring in. There could be, lots of scalarized neutron stars and black holes. But yes, what would they do to jig up this binary signal for me? I think that the verdict there is still playing out. Now, but some of the problems with these contaminants is that they can vary from one neutron star merger to another, right? Now, the dark matter particle mass may be common, so that's less of a problem. But the extent to which the accretion of dark matter happens in different neutron stars, that can vary, and that's the problem. The mass radius plots, will no longer conform to the nice ones that we see from essentially pure neutron star, right? But if there are other influences that are common, for example, if the true theory of gravity is not really Einstein's general relativity but something else, then it's very likely that that effect will be common to all of these boundaries. So those may be easier to constrain by doing population studies. I may not talk much about these contaminants anymore, but I thought I will leave it out there. So we'll focus mostly on neutron stars without those contaminants. And as you can tell, so these are objects, and I know there's a diverse crowd, so this is my only basic slide on neutron stars, perhaps. But these can have radius of something like 11 to 13 kilometers for about a 1.4 solar mass star. And given that they are essentially born out of what was iron ash in the core of a dying star, and And if you solve the Tolman-Oppenheimer-Volkov equation with a reasonable polytropic equation of state, but again, you can assume that maybe it is supported by neutron density pressure, so you know the pressure goes like density to the 4/3 and so on. You would expect that, yeah, both the pressure and density will drop as you go towards the surface. So the surface densities are similar to densities that you'd see in our labs. So 30 to 50% of the nuclear saturation density, where loosely speaking, that rho naught is roughly the density of lead in a terrestrial lab. So here you can therefore expect iron, but in this case in the ionized form, and that's because we are neutron star temperatures are of the order of tens of MeV, and in contrast, the electronic binding energy to atoms in our labs is of the order of 10-ish eV, right? So therefore you would expect the electrons here to be in a degenerate state, and that is why, so their wave functions are overlapping, and they're not tied to any particular nucleus, right? So this is an ion lattice permeated by degenerate electrons, but as you go deeper, the density rises, and these ions start dissolving into individual nuclei themselves. And as the pressure increases further down, even these nuclei will dissolve. Before they dissolve, you'll have nuclei rich with neutrons taking on odd shapes like pasta and lasagna that you may have heard of. But eventually, most of the star here, for something like 1.4 solar mass star, would be a neutron-proton Fermi fluid with perhaps mostly neutron, nearly homogeneous neutron matter, maybe up to 10-ish% of protons, and a similar number of electrons for neutrality. Deeper in the core depends on the total mass of the neutron, but if the mass is large enough and the equation of state is somewhat soft, meaning nuclear-nuclear interactions at close distances, mediated by vector mesons, are not very repulsive, let's say, then you can have a situation that in the core there is a phase transition from neutron matter to a coordinate plasma. But so what can we do in constraining any of these models for the interior of a neutron star? In gravitational waves, what we have been doing all along is observing chirp signals, right? But this was a pretty early paper by Reed et al., followed up by, and again, I'm sorry that I'm not being comprehensive in surveying all of the literature in this field. So if I miss your paper, apologies. Please feel free to speak up in the middle of the talk or in the discussions. So here, we're showing what happens if the equation of state of the neutron star is soft, meaning not much pressure for the same density, and up there, if it is stiff. So the neutron star exerts large enough pressure for the same density, and this is a middle of the road equation of state. But if the equation of state is soft, then these plus and cross polarizations of the strain in solid from the neutron star are not going to be very different from the point particle waveforms or even binary black hole waveforms because you don't have much matter extent in which you can induce further quadrupolar modes and radiation, right? So the dephasing will not be that much different compared to binary black hole waveform of similar masses. But if it is stiff, then the dephasing will be large, and in the binary black hole case, the merger happens there, whereas for the binary neutron star case with stiff equation of state, the merger is happening somewhere here early on, and then what you have is not a damped, sharply damped sinusoids of quasi-normal modes that last for about a millisecond, but rather an extended post-merger signal, which can last anywhere between maybe 20 milliseconds to 100 milliseconds, depending on the numerical relativity matter group you're talking to, right? That's a point that we should come back perhaps to discussions, that it's really important that we get an emerging consensus among the various matter groups on the actual physical effects as opposed to code-related systematics. Okay. So yeah, here in the pressure density diagram, the stiffer equations of state will be curves that are somewhat higher, and the softer ones will be on the lower end. Now, we talked about dephasing, so that indeed is an observable, but that can be translated into this tidal deformability of a neutron star. These are isocurvature contours taken from this paper, but Flanagan and Hindrer and others have studied how much you can deform a neutron star because of its the external tidal field of its companion, how that can actually introduce a dephasing through a parameter called the tidal deformability parameter, which the dimensional kind takes values anywhere between maybe somewhat less than 100 to about 100,000 for most matter that we can think of. With LIGO Virgo, we have constrained this, and you already saw these plots. I'm not going to spend too much time, but basically there is an error region here and it depends on whether you take the stars to be spinning or not as your prior. But for non-spinning with 90% confidence, you say that for a 1.4 solar mass, this tidal deformability will have a value of 190 or so, but with large error bars. Okay? In the mass radius plane, this can be translated to these kind of error regions. And of course, this study has been complemented by observations of the compactness of neutron stars by NICER. We have also drawn conclusions from the kilonova spectrum accompanying GW17017. And so when you look at all those data sets, the roughly consistent picture that emerges is that, yeah, the neutron-neutron repulsion at close distances, by close I mean like quarter of a Fermi, right, it exists. It's not small, because if it were small, then the lambda would have been even smaller, and the kilonova, the ejector material would have been less, and the luminosity of the kilonova would have been less. But on the other hand, it is not too stiff either. Otherwise, this radii would have been larger, and other equations of state like H4 or MS1 would not have been ruled out. So although these are relatively broad, but they were still successful in ruling out some of the stiffer equations of state. So, but now mapping this macroscopic observables to microscopic physics, what exactly are we getting at, right? So to understand that, you can plot the binding energy per nucleon as a function of the nucleon density, and terrestrial matter is replete with nuclei that have roughly equal numbers of neutrons and protons, right? So that's what we call, if they're equal, then that's what we call symmetric nuclear matter. In other words, there is an isospin symmetry or near symmetry in these atomic nuclei that we see in our labs. So the number density in neutrons is the same as number density in protons here. But as you go to heavier nuclei, and certainly in the neutron star, this asymmetry is much more pronounced, right? There's many more neutrons than protons. But if you want to connect observations made in labs, which are actually done with symmetric nuclear matter, to those made with neutron stars, then you have to bridge this gap because their binding energy profiles are different, right? So they're not only, this profile, this binding energy is not only a function of the isospin asymmetry, this delta parameter, but also it's a function of the nucleonic density, right? So in other words, neutron stars actually, if we can model this gap, then we can use it to understand nuclear physics at high densities, which is great because, well, lattice QCD won't help us, although it's a beautiful theory because that actually deals with much higher densities, orders of magnitude higher densities. But you can maybe learn something from perturbations of QCD like chiral effective field theory, which operates typically at close to nuclear saturation density, somewhat below it, but people have extended it to make predictions at somewhat higher densities above the nuclear saturation density. And so those predictions can be tested by complementing terrestrial observations with astrophysical observations. You can model it theoretically like this. This is one of many models. You can call this a meta model where, again, because we want to map this to macroscopic variables, we bring in the pressure as a function of a density-like parameter, so energy per particle of nuclear matter, E0. But the pressure and that density both are functions of the neutron or nucleonic density inside a neutron star, rho, and the asymmetry, the isospin asymmetry parameter, delta. So you're expanding these quantities not only in orders of the isospin asymmetry, delta, but also about the nuclear saturation density. So you expand rho about the saturation density, and so you bring in, so chi here is basically, how denser are you getting, basically how deeper are you getting into the neutron star, and you can expand these pressure and density variables in terms of, therefore, both chi, the density parameter, as well as the asymmetry parameter. And there are two of these parameters that are possible to constrain with our observations are the symmetry energy, E sim, which is this leading order correction in the because of the isospin asymmetry, right? And the slope of that parameter when you expand it about the nuclear saturation density. So question is, can we constrain these leading order parameters, L and E sim? There are others which are more difficult to constrain, and it turns out, as you'll see, that we don't do that much of a good job of constraining them. As an illustration, this is a work that I was a part of where we started making these mass radius observational profiles, beginning with just the maximum mass in a pulsar observation, but then adding GW observations, again, mainly from 1708-17, but we included data also from the secondary component of 1908-14, which is very likely a neutron star in maybe an NSBH binary, but also 1904-25, which also may be heterogeneous, but maybe it's a double BNS as well. But these are at larger distances than the 40 megaparsec even. But anyway, so 1708-17 dominates this, but as you include this additional observation, you see how the error bars shrink, and NICER helps in shrinking, but also moves it a bit on the stiffer side. That is something that some of you have all, perhaps observed in other data sets. But at the end of the day, and yeah, this was led by Bhaskar, who is a Humboldt Fellow now in Hamburg. So we landed up constraining basically all of those EO state parameters in that meta model I showed a couple of slides ago. But really, if you look at it, it's that symmetry energy slope parameter that we don't necessarily make it more precise, but with GW and NICER, it seems that this value is smaller than what just the maximum mass pulsar would have had us believe. This has some consequence, and this is still within error bars, but if this feature stays with future observation, it will tell us that the neutron matter is not as stiff. The pressure exerted is somewhat less than what the single observation would have told us. This has direct impact. Other parameters don't really make much of a difference in the radius measurement, but this comes hand in hand basically also with the radius measurement. It tells you that for a 1.4 solar mass, because the equation of state is not that stiff, the radius also will be somewhat smaller, or the object will be a little more compact. I have to also point out that to construct these posteriors, we had to use a different parameterization for the core, the inner core of the neutron star here. We basically let the astrophysical data guide us. We took it to be a piecewise polytrope with three polytropes, gamma 1, gamma 2, gamma 3. And that is because nuclear models lose predictability at those high densities. If we did not allow for this additional parameterization in the dense part of the star, then these other numbers at low densities were getting larger biases. In fact, to the extent that even the vanilla, relativistic mean field theory models were getting, to some extent, deprioritized. But allowing for a different parameterization of the core gives us numbers that are, again, as maybe more consistent with the kilonova and NICER observations, but they do suggest the following, that at larger densities, deeper in the core, there is some evidence that that there is a transition in the equational state. It perhaps gets softer, basically. Okay, now in the future, we are going to build detectors that see deeper. This plot also you may have seen from the Cosmic Explorer science case. We'll see all the binary black hole mergers that occur, but also most of the binary neutron stars. So one of the papers, this is something I just alluded to on my second slide, but basically this is showing how they are using multibanding sampling, multibanding sampling, something like what even GST-LAL does nowadays, but also constructing SVD bases for their templates, projecting the signals on those bases, and then using relative binning or heterodyning for likelihood sampling in the parameter space, and then finding these transformers to compress the GW data and the equational state possibilities better using neural networks, and then using normalizing flows to draw inferences. So there are details which I'll just ask you to go to this paper to read, but they're essentially preparing for observing something like 100,000 binary neutron star events per year in that era, but they're not going to wait for that era, right? Because they can already do some simulations and make the science case better with this facility today, right? Because the other challenge is not just these numbers, but the fact that every time you're sampling the equational state parameter space, you have to solve a TOV equation. And that also is a lot of number crunching. But at the end of the day, they succeeded to show that they injected some true equational state in this deep purple here, and with hours of computation, they were able to constrain from their observation what was observed to be in this somewhat broader patch. So they make some simplifications. So they admit that this is not fully kosher. It needs further development to be applicable to real data, but at least the first steps are being taken. They also go on to construct all of these posteriors, including the tidal deformability and the delta lambda, which is basically arises, for example, if the two masses in the binary are different. There is another work by Abak et al. From the, I think, Team Dietrich and Jonathan Gehr group, where they show that you can actually, because the signal to noise ratio will be so much better in future detectors, that you can use the signals themselves to extrapolate beyond the known post-Newtonian corrections. So those corrections are known up to 7.5 pn now, but you can go to and include terms at 8 pn, 8.5, all the way to 9 pn. So you have like 3 additional parameters there. You're modeling this, the phase terms in terms of polynomials and additional tidal deformability parameters, which they call kappa here. The A and B are just the secondary and primary neutron star components in the binary. But they're showing that using this kind of a polynomial fit, they are able to calibrate. And with more observations, so going from 1 event to 50 to 100, they're able to shrink this error bar in the estimation of these additional post-Newtonian parameters better. Okay, can I take maybe 5 more minutes? Okay, thanks. And I'm embarking on the last part of my talk. But if you are able to measure the equational state better, then, and if indeed you're expecting lots of sources, then what else can you do? So here, I'm basically preparing, for example, to do cosmology, but now increasing the challenge a notch by saying that what if you don't have electromagnetic counterparts, or even if you do, that they're not actually going to give you a reliable redshift, right? So the neutron stars are on their own, meaning the only recourse you have is to the gravitational signal. So if for nothing else, just for this academic exercise that gravitational waves alone would be able to teach what all, this may be interesting. But it hinges on a smart idea that Messenger and Reed came up with more than a decade ago, where they realized that because this dimensional tidal deformability parameter is just a number, it does not get redshifted. So in that sense, it's like a standard candle. just by measuring it from the waveforms we see here, we can actually extract or get a measure for the source mass, the source frame mass of the binary components. So the idea is that, yeah, if you solve your TOV equations for various equations of state families, right, and you get for each equation of state, you get a different curve for in the lambda versus the component mass plane. Of course, that can be translated into radius versus mass, but ignore this bottom panel for a second. But if you knew the equation of state somehow, so that's an assumption, but suppose you knew that true equation of state is this top one, then the moment you measure the lambda, let's say to be 100, you go all the way down on this horizontal line, and you find that, okay, the mass is 2 point some, right? But of course, we don't know the equation of state that precisely, but you don't have to. The idea that we and some other groups put forward was that we will simultaneously measure both the equation of state and the redshift. Okay, but we can be helped by another consideration, which is basically what is used also by the binary black hole people that Archana nicely summarized, which is use the mass spectrum. So, but there again, you may say we don't know what is the true mass distribution of neutron stars. It could be Gaussian, it could be like this ATN of catalog, but these are not necessarily in double neutron star binary systems, right? So which one would you trust? Again, you don't have to. You just say that we will use different models for the mass distribution and see which of these is most consistent with the data. Again, assuming we have hundreds of sources. And I think Isha's promised us that, right? So, all right. So so that's what we do. We run this experiment with, we experiment with two different types of populations, Gaussian only or double Gaussian. These are the injected parameters, true values, but these are the somewhat broad priors. And we also allow for some redshift distribution. So evolution of the redshift, of the rate with z as 1 plus z to the gamma. So we took gamma to 0 here, no redshift evolution. And these are the widths of the distribution, the relative combinations. The details here you can ignore. I'll just zoom into some of these plots. What we show is that there are two kinds of curves, green and maybe maroon or orange. Okay, so 50 events in 05 like sensitivity for Hanford, Livingston, and Virgo. So we use EOS, the equational state information, that messenger read trick to get the orange curve. So the equational state actually information improves over just the mass spectrum idea. Again, similar to the binary black hole, right? But only for the mean of the primary mode in measuring this mu. Okay, for other parameters like the spread in the first mode, the relative amplitudes of the first and the second mode, W, or the mean and spread of the second mode, it doesn't make a difference. But the other place it makes a difference, holding in the equational state information, is the measurement of H0. Here we have 50 events, and again, this is not CE sensitivity. We did not do CE because we did not have the solution that the Glasgow group has just developed. Maybe that's the next thing they will do. They will actually do it, honest to God, CE simulation, right? So our signals are shorter and closer, but we show that, yeah, you can get 10% like improvement. We tried it for 3 different equation of state, actually priors. We assumed the knowledge of equation of state to be very precise, less precise, and we got different estimates. Again, this was led by Tathagata Ghosh. Shashwat is also a collaborator on this work. Okay, I'm going to end with a couple of slides. First, I was talking about tidal deformability, but then there is also tidal heating. Tidal heating, if there are no hyperons in neutron stars, then it is expected to be minuscule. So you can ignore any tidal dissipation happening in the neutron star. The bottom line is that if there are hyperons present even in the core of the neutron star, they increase the viscosity because the presence of hyperons reduces the leptonic interactions of nucleons, neutrons and protons. And in the process, it allows neutrons to travel longer distances. So the mean free length increases. You basically have momentum carriers that are going to travel longer distances and therefore contribute to the dissipation. And when there is more so yeah, this kind of reaction reduces, the neutron, lambda, or proton, sigma, those interactions increase. The bulk viscosity increases. The flux, because of that, the gravitational radiation flux also increases because of this. The dependencies on the mass, radius, and the distance of separation in the binary, the F mode frequency, and the tidal coupling strength, all of that behavior is given here. But this is the upshot. Namely, as a function of the post-Newton expansion parameter V, or basically the frequency to the 1/3, the dephasing, because of tidal dissipation, is shown in the solid line. For comparison, we have also shown the dashed line behavior for the tidal deformability. And it turns out that tidal heating for higher masses can actually get comparable to tidal deformability. And this is, I would say, still preliminary. We did make some approximations here for the modeling. Oops. Okay. But if this holds out in a more robust simulation, what it would mean is that if you do not account for tidal heating, then you will miscalculate the tidal deformability of such a star, at 2 solar mass to be higher than its true value. Okay, so in conclusion, we were able to constrain the symmetry energy slope reasonably well with past observations. The nuclear physics message here is that the mid-range tidal deformability value is consistent with kilonova spectra. The quick reddening of that spectra basically means that it is rich in elements with lots of neutrons and less electrons. This is consistent with the fact that the equation of state is not very soft. We also learned, and this I didn't talk about, but the SGRB jets can be very complex. Arun talked about it. With future observations, multi-messenger observations, we can further this understanding to check whether we can get a better handle on the circumboundary environment, how electron-rich it can be or not, what its host is like. We just have basically one observation so far. Are the hosts predominantly elliptical or star-forming, etc., right? Parameter estimation will improve, hopefully, with louder signals. But then we just saw that we'll need smarter data processing to deal with all the big volumes of data that will come at us. Growing SNRs also means that systematics will be in the focus now, which is why I was making the case that perhaps we should have a ninja-style head-to-head test of NR matter cores across different groups to make sure that the differences they see, even in the lifetime of the post-merger, is not because, we want to make sure that whatever the differences are just core systematics and not physics, basically. Yeah, that's the idea. And then, I'll leave you with this question. I just put this out of how to do cosmology, but is it indeed the case that you can do, you can constrain the equation of state of neutron star purely from gravitational waves alone? What is the limit of that, basically? And then if you do cosmology, of course, it will come with its own systematics, but how bad can they be? Thank you.
Thank you, Sukanta, for a very nice, clear overview. Maybe we have time for one burning question if someone wants to take the opportunity.
Hi, on your slide 4, you showed a gravitational wave signal of the post-merger part. So I wanted to ask what kind of mechanisms are responsible for those modulations in the post-merger part of the signal, especially in the case of stiff equation of state.
Yeah, so I think the primary mode here is the quadrupolar mode, right? So the bar mode. I mean, you have two neutron stars, or whatever remains of them after maybe some tidal disruption, right? That are now, because of the gravity, they're coming closer, right? But they're also still orbiting the common center of mass, right? So you have a quadrupolar distribution that is still, time varying. So that tells us, for example, about how compact the stars can get, right, at those densities.
So I think you mentioned that the stars have already merged here. So after that, I would expect that there would be some oscillation mode which are responsible for this, or like after the merger, for example, transition can also happen. So I was just wondering what kind of mechanism is mainly responsible for these kind of signals.
Right. So there are also additional modes that one sees in the numerical relativity simulations. And I don't know, do we have an expert here on post-merger oscillations who know more about the origin of the secondary peak? Or there is also mode mixing, by the way, and we see signatures of them as well.
So I'm saying, sir, there may be possibility of like extra modes, for example, P modes and G modes.
The question is, what is actually seen in the numerical relativity solutions? Because, yeah, in principle, you may have them. And if you have G modes, indeed, they are bulk modes that can capture information about any phase transitions that would happen. But I don't know whether they are the dominant modes, right? That show up.
In particular, if we are, for example, interested in seeing the signature of hadron-quark phase transition, then in that case, the most sensitive mode is actually the G mode. So,
sure. Yeah. But I'm not sure whether that actually is any of the dominant modes that's seen.
So I think we have to distinguish the in spiral, at the time of in spiral, when the natural oscillation neutron stars couple with the binary forcing, that I think probably we are talking about that. In the post-merger case also, for the long-lived remnant, which will form neutron star, at some point we will observe that, but that's that happens after the remnant becomes very close to the neutron star in the final remnant. But the question that you're asking is about the post-merger, where I think there is a model by Takami and Rezola, right, where they model the post-merger as a two-body attached with a spring which is rotating. That provides rough, but I don't think that's the way we should go forward.
Yeah,
full basic modeling.
Yes, I'm aware of that model, but I also know that not everybody conforms with that interpretation. So that is why I left it out. Yeah.
So in the interest of time, let's continue this in the discussion session.
Thanks.
And thanks, Sukanta, once again.